and click on your video. I'll go stand by the board. Step first. I'll get them in a second. All right, you can admit them in a second. Just stand back there.
Seems fine.
Yeah, I think I'll go ahead and admit those kids and get some. Anybody?
Mm-hmm.
Fast food delivery, if you get up to 3 minutes, go get that.
Hello, everyone. We'll be getting started pretty soon. It's charging. Oh, yeah. Yeah. Okay. Yeah. So yes, we'll be getting started in a couple of minutes. Okay. So okay, so hi everyone. So welcome to today's Math Divulged lesson. So before we start on math today, oh, by the way, I should just check. You can all hear me, right? Okay, good. You can hear me. So before we get started on math, Brian will say something, I think. So
Okay, so before we get started, we all know what this country has been finally been paying attention to. So let's give a moment of silence to George Floyd, Ahmaud Arbery, Breonna Taylor, Tony McDade, and countless other Black lives lost due to police violence and systematic racism, and say that Black Lives Matter. Today would have been Breonna Taylor's birthday, 27th birthday. She was saving lives during the pandemic as an EMT. She would have saved so many more lives if she would have been alive today, but her life was taken away by a police officer. And George Floyd, who was killed and murdered in Minneapolis, the officers involved in his murder were charged, but let's not forget that this is the result of having fought for it. Eric Garner, who said the same last words, "I can't breathe," the officer who killed him was not charged, was not indicted. Philando Castile, who was killed in the same state, Minnesota, the officer who murdered him was not indicted. So we must always demand justice and accountability and use our privilege, our racial privilege, and our, in the context of us learning math, our educational privileges, to channel those privileges into fighting for Black Lives Matter, fighting for equity, so that another life does not end up a hashtag. The officers who killed Breonna Taylor have not been charged yet. So we must demand justice, and we must demand justice and accountability and change the way this country does policing so that not another innocent life is taken away. Okay, thank you.
So let's all remember, as a tool, mathematics, you can use it. It's a tool, so people can use it for good or for bad. So it's important to use mathematics for good to help there, hopefully there can be, justice, more justice in the world, hopefully. But so I guess let's move on to math. So, okay, let's move on to math. So, okay, today's seminar is about basic abstract algebra. And so, also I should just say, please, if you have any questions, do not direct them to me, because then I would have to interrupt my teaching to get over to the keyboard and tap, tap, tap away. So please direct your questions to Brian or to Justin or to Naveen, and they will happily answer your questions, and they will do so more efficiently than you would get your answers if you asked me. So yeah, please direct questions to them. Okay, so let's get started on the math. So okay, so basic abstract algebra. So, well, abstract algebra. Basically, it's like algebra, except it's abstract. And so, some fundamental structures in abstract algebra are called groups. So basically, let's start thinking about, just as sort of an example, to sort of give you motivation and help you understand. Let's think about algebra in the simplest type of algebra. Just think about equations just equations, linear equations in a single variable on the integers, and they don't even have any multiplication, just addition. So you might have an equation like x plus 3 equals 7, just the absolute simplest kind of thing. And of course, this is trivial, but you would solve this without even thinking. You'd just be like, oh, okay, sure. Subtract 3 from both sides, and you get x is 7 minus 3, which is 4, sure. But, let's think carefully about what's going on here. Basically, don't think, because subtraction sort of is just like derived, from addition. So let's just think about this in terms of just the integers equipped with an operation addition. And basically, I want it to be a binary operation, which just means basically binary, it takes in two things and outputs one thing. Binary for the two things it takes in. And so basically, if you wanted to solve an equation like this, you would start by adding -3 to both sides. Okay, then you use the fact, that addition is associative. Now, you use the fact that -3 is an inverse of 3, an additive inverse, to get that this is 0. And then we use the fact that 0 is an identity to get that x plus 0, regardless of what x is x. And so you get that x is 7 plus -3, which is 4. But the point is you could evaluate that. And this is following the exposition in a book I have, which is a pretty good book. If you, it was, this is a pretty good book. So this is the source for some of the material. So, but there are lots of good books about this stuff, but yeah. And so let's just think more generally about if we have just some set, a non-empty set G, and some binary operation star. And so basically we want star to be associative. So, okay, non-empty set G and binary operation star on G. So we want it to be associative. And we want there to be an identity element, which I'll denote by iota, the Greek letter iota, so that basically we want there to be an identity that where anything starred with iota on either side is just the same thing. So x star iota equals x and iota star x equals x. And so star, yeah, as Brian is saying, this is sort of more generally like star, in this case, star would be plus, as Brian is saying. And then finally, we want every element to have an inverse. So for every x, there's a y, so that x star y is y star x equals iota. And so having all this, we say that G, and equipped with star, is a group. Or you could say that G is a group under star. Or sometimes it's sort of obvious from the context what the operation is. And then sometimes you might be lazy and just say G is a group. But like the group is the set and the operation. But sometimes the operation is just obvious. So now notice one thing. There's a certain axiom that you might think that is true for addition that is not one of the group axioms. And so that axiom is commutative. A group in general does not have to be commutative. The operation doesn't have to be commutative. And so if you have a group, and the operation is commutative, then we say the group is abelian. A-B-E-L-I-A-N, after the mathematician Abel, or however you say his name. And otherwise, I guess you would say it's non-abelian or whatever. I guess non-abelian is the right word, but yeah, the point is some groups are abelian, other groups aren't. You don't just assume that the group has a commutative operation just because it's a group. And so we'll definitely see some example. I'll definitely show you, you'll see that groups don't have to be abelian. There are groups where the operation isn't commutative, and you want to think about those groups. Those are the spice of groups, if you will, the interesting things, perhaps, in some sense, because like if you have finite groups, just finite abelian groups are not that interesting. Like you can just sort of say what they all are, basically. But and there's not that much variety to their structure. But finite groups as a whole, there are more weird things, including there's one group that's so large it's called the monster group, which I'll tell you more about later. But there are interesting things, and so you don't get to assume the operation is commutative. So deal with it. Some operations aren't commutative. And if you've seen some stuff with matrices, you know that matrix multiplication isn't commutative, and that's an example. But let's see some examples of groups. So here's an example of a group. The integers, what is this marker? Bad marker. The integers under addition. And you can just check that it holds. And that was basically the motivational example. So of course it holds. And 0 is the identity, and negatives correspond to inverses. And of course, more examples could be the rational numbers under addition, the real numbers under addition, the complex numbers under addition. Another example could be the positive real numbers under multiplication. You can check that that's a group. The identity is 1, taking inverses corresponds to reciprocals. You could have, the non-zero real numbers under multiplication. Here now, another example could be the integers modulo n under addition, mod n, for any positive integer n. And I'm going to write the integers modulo n as this weird notation, like it looks weird. It's z mod nz is how you would write the group of integers, like the set of integers modulo n. And this notation will be consistent with some things later on, but it might look weird now, but you'll see more later. So these are some examples of groups. And in particular, these groups are all abelian groups, it turns out. Addition is commutative. Multiplication of real numbers is commutative. Addition mod n is commutative. So let me tell you an example of something that is not a group. An example of something that is not a group would be the real numbers under multiplication. Sure, it's associative. And then sure, you have an identity, and the only choice for the identity element, you'd have to pick 1. There's no other real number that when you multiply it by anything, you get the same thing. But now look, what would be an inverse for 0? 0 times something is 1. What are you going to do? So this is an example of something that's not a group. Another example of something that's not a group could be the positive integers under multiplication. Again, it's associative. You have an identity, but then what do you do for and for an inverse for 2? 1/2 isn't an integer. Or another example could be the positive real numbers under addition. there's not an identity element. 0 isn't a positive real number. What real number, you're not going to have an identity element for this operation. If I want 1 plus x equals 1, then x is going to be 0, but then where are you? 0 is not a positive real number. So these are groups. These are not groups. And, you could even have something that isn't even associative. You could just have something like, you would just make up some really weird operation like, let's have two elements A and B and define some random operation like A star A is B, and A star B is B, and B star A is A, and let's, maybe B star B, you want it to be B. You can make up a binary operation to be whatever you want, but you're probably not just going to write down some random thing and have it be a group. And here's an example of something that isn't even associative. A star A is B star A, which is A. A star A is A star B, which is B. So this isn't associative, so it's definitely not a group. So this is, here, these are some examples of groups versus not groups. And so, but all the things I've shown you so far that actually were groups were abelian groups. The operation was commutative. And so you might be getting a little bit like, oh, sure, Luke said that there are non-abelian groups. Luke said that there are groups whose operations aren't commutative, but he must just be kidding. Maybe he's just pulling our leg. Maybe he's just joking. But no, I'm not just joking. There really are such groups. So let me give you an example. So an example, let's take n to be an integer at least 3. So now consider a regular n-gon. So maybe n is equal to 4 and I have a square. So now I'm going to define a group Dn, the dihedral group of an, I guess you would, there's a bit of an annoyance with notation, but so basically the dihedral group, and this is sort of a very important example for motivational purposes. The dihedral group is sort of all the symmetries of this n-gon. So like all the ways you can spin it around to put it back to its original location, but maybe not with the corners in the same order. So one example, and this really is a group, and notice that it doesn't matter like what we do, like all that matters is how it starts and how it ends. So maybe I should label the corners like, W, X, Y, Z, and say it only matters how the corners get permuted because the corners, determine the whole thing. But like the point is you have some ways it behaves and it's not necessarily commutative. So here's one element of the dihedral group. This element would be do nothing. That's an element. Oh, also, I should tell you what the operation is. So the operation is, do one thing and then the other. And so, if I have some element A and some element B, then I could just write it as A star B. And I want to say that this is going to be do B first and then A. I want to say that it's going to be that way. So, so it's sort of just do one thing and then the other is the operation. And I claim that this really is a group. And so, so it's associative, if you do one thing and then you do another and then you do another, then you've done all three things. And it doesn't matter, if I rotate it and then I flip it and then I flip it again, or if I rotate it, and then I flip it, and then I flip it again. It doesn't matter how you parenthesize, it's associative. And then the identity would be do nothing, which is a perfectly legitimate thing to do. And then the inverse is just undo whatever you just did, reverse time. So maybe that's a little confusing. So let me give you some explicit examples of things. So one element of the dihedral group would be rotate the square 90 degrees. So maybe if it started out looking like this, it would end up looking, like this. That would be, and then you could just put it back down where it was. That's an element. Or another element could be flip the square over this way. And so now it might look like this. So it turns out that this group in total has 8 elements. Basically, there are 4 ways where you don't flip it, which is like do nothing or flip or turn it a quarter turn or 2 quarter turns or 3 quarter turns. Or you can flip it and then do nothing, or flip it and then a quarter turn, or flip it and then 2 quarter turns, or flip it and then 3 quarter turns. And so in general, this group will have 2n elements. And so now at last, I can give you an example of a group that is not abelian. So let's consider those 2 elements I just told you. Let's consider the rotate at 90 degrees clockwise, and then let's consider the flip over this vertical axis. So, sort of a mirror image. So, okay, if we do the mirror image and then the rotation, if I do the mirror image first, I get this. Then if I rotate this 90 degrees, you can just see you're going to end up with this. So you're going to end up with y in the upper left, z in the lower left, and x in the upper right, and w in the lower right. On the other hand, if you do the rotation first, you get this. And then if you flip that over this horizontal axis, now look what you've got. Looks like that. And now look, you did it in one order and you got this. You did it in the other order, you got this. If this were an abelian group, you would have gotten the same thing, but you didn't get the same thing. Look, this one has x in the upper right, this one has x in the lower left. They're 180 degrees off from each other. So it's not abelian. If it were, you would have gotten the same thing. So you didn't get the same thing, so it's not abelian. So this group, in this case, it's D4, is an example of a non-abelian group. And I think you should have that Dn, for any n greater than or equal to 3, is not abelian. You should have, I think. So this is an example. So this D4 is an example of a group that is not abelian. So another example of a group would be Sn, all the permutations. And so this is, before I move on, this is an example of how you could have a group acting on something. Like you have a group acting on all the set of possible positions of the square. And so actually a nice picture from Wikipedia of like all the different positions you could put a stop sign in under all the elements of D8. So you could think of D8 as acting on this set. It would look like this. You can see that, you could put a stop sign in a lot of different positions. And so, the identity element would just leave all of those alone. And then maybe the reflect over the horizontal axis might send, this one to that one. And, then it would send, maybe that one to something to, I guess, that one, etc. And you could think of the dihedral group as acting on these. And so, this is an example of, if you think of the dihedral group as kind of hard to visualize, maybe this will help. So, and so another example, and so, yeah, so you could define formally what it means by a group action, but I won't bother to do that. You can find that in a textbook or whatever. But my goal today is not to, read to you out of a textbook and hope that you're going to get the same experience that you would in a college class. This is not supposed to be a college class where you have a textbook and then the professor assigns you homework or whatever. Today's seminar is more of a sales pitch for math rather than a college class. So my goal is not just to read to you out of the textbook in today's class. Okay, so yeah, I don't want to just read you out of the textbook in today's class. I want to show you, I can sort of skip some details in a way that a textbook wouldn't. So anyway, another example could be Sn, which is all permutations of the set 1 through n. And a permutation is basically a bijection from a set to itself. Basically, it just means like, you could have this permutation is like, it's a function basically. I'm gonna denote this set by bracket n. So for example, bracket 4 is the set 1, 2, 3, 4. And so, if you have a function from bracket n to bracket n. So for example, an example of an element of S4 could be, 1, 2, 3, 4, and then maybe 1 goes to 4, and 2 maybe goes to itself, and then 3 maybe goes to 1, and 4 goes to 3. So you have the same numbers, just maybe in a different order. And so, and then the operation is composition. So, if to combine the functions f and g, you compose them to get a new function f composed with g. That's just like f composed with g of a number x is f of g of x. And so composition is the operation here. And this really is a group for any positive integer n. The identity, and you can just, it's associative. It has an identity, which is just the identity function sending every number to itself. So, 1, 2, 3, 4, for example, just 1 maps to 1, 2 maps to 2, 3 maps to 3, 4 maps to 4. And then every function has an inverse, because in this set, every function has an inverse because we said they're permutations. So, if I were to just erase all these arrows, and then just draw them all the other way, I could get an inverse to this function. And then, you could rearrange them to make it in a more plausible order, but you can see this is, you just 1 maps to 3, 2 maps to 2, 3 maps to 4, 4 maps to 1. And so you can check that they really do all have inverses, and so this is a bona fide group. And so you can check that this too isn't abelian. It is not abelian. So this is another example for n greater than or equal to 3, I should say. And so this is another example of a non-abelian group. And another example of a group, which is a little more maybe technical, but it'll show up again briefly later. So I want to, but don't worry too much about it if you don't follow me with this, would be that basically, and notice I said earlier, so Dn has 2n elements. This group Sn has n factorial elements. Now, another thing, every element of Sn can be built up from transpositions, which is basically just like switch two things. So for example, if I wanted to build up this element that I told you about earlier, this 1 maps to 4, 2 maps to 2, 3 maps to 1, 4 maps to 3. This element that I told you about earlier from transpositions, I could, for example, do, well, swap 3 and 1. So swap 3 and 1. So 1 maps to 3 and 3 maps to 1, but everything else is unchanged. And then swap 3 and 4. So 3 maps to 4 and 4 maps to 3, but everything else, is unchanged, and voila. And you could do this, you could write any element as a composition of 0 or more transpositions. And I could have done this in many different ways, maybe a way that wasn't maybe the most efficient way I could have done. But it turns out that if you write it in 2 different ways as transpositions, you always get the same parity. It's always either even or odd. So, this element, I wrote it as 2 transpositions. So any way I write it as a composition of transpositions, I would get an even number. And this is not obvious, but I'm not going to prove it today. You can prove it yourself later. Or maybe not, but maybe you might not want to, but you can either prove it to yourself or look it up online. If you look up the parity theorem, I guess is what they call it, or whatever. But that's not the most important thing. The important thing is that that is true. And so it turns out that if you focus on just the ones with an even number of transpositions, you get another group called An. This is the symmetric group over here, this Sn. This is the alternating group. And then this has n factorial over 2 elements for any positive integer n, except it has 1 element for n equals 1 instead of 1/2, because, what would having half an element mean? And, this is sort of an example of a general phenomenon. But yeah, this fact about parity, you don't have, don't worry about the fact about parity. The point is it's true. So, but yeah, you can look it up if you want to, and you can prove it to yourself, but don't worry about that. Anyway, the point is, I have this An is a group that is, and it's a subset of Sn, and it's under the same operation, this function composition. And so An is a subgroup. I know, such inventive. Of Sn, such inventive terminology, subgroup. And so, it's a subset and it's a group under the same operation. So it's a subgroup. And so you could define subgroup in general. And it means what you think it means. It means that you have a group and then you have a group that is a subset of it, that is a group under the same operation. And so there are some trivial examples, like any group is a subgroup of itself, or for any group, if you take the set that's just the identity element, that's a subgroup. Braces are kind of annoying to draw. This is, this is a subgroup of the group as a whole. But there are lots of examples of subgroups. Another example would be for the group of integers the group of integers under addition. You could take the set of even integers under addition, or you could take the set of multiples of 93 under addition. But the important part is that when you do the operation on two things in the subgroup, it has to stay in the subgroup. So if I wanted to take the set of all, if I wanted to claim there was a subgroup of Z that was the odd integers, well, no. I mean, that wouldn't have an identity, but even if I took like 0 and then all the odd integers, that wouldn't be a group, because 1 plus 1 is not odd. 2 is not odd, so that's not a subgroup because it isn't closed under the operation. And then it has to also contain the inverses of everything in it, and so those would be subgroups. Now, there's a special kind of subgroup of a group that will behave especially nicely. So that would be a normal subgroup. And when I say normal, I don't just mean like normal as in usual or expected. It's a math word. So a normal subgroup. And now the definition of normal subgroup looks kind of weird at first. So let me try to motivate it, because it's kind of important. So you have modular arithmetic. And so, you say that A is, for a positive integer n, you say that A is congruent to B mod n if A minus B is a multiple of n. Okay, sure. So let's look at this as group theory. You have A plus the inverse of B is an element of nz. And so let's think, instead of looking at it as mod n, let's look at it as nz is a subgroup of the whole group. Now, there's an interesting thing that also, a new thing. I'm going to start writing the group operation as just juxtaposition, just like as if it were multiplication, because star is annoying to write or whatever, and it's not the most useful way of thinking of it. And I'll also write inverses as like a -1 power. So let's just ask a question. What's the inverse of the product of, when I say product, I mean like whatever the group operation is. In a general group, what is the inverse of a product? Well, you might say it's the product of the inverses, and you might be you're kind of right, but in what order? So if you want to say that the inverse of an element gh is the inverse of g times the inverse of h in that order, no, that is not necessarily true. You have to take it in the other order. The reason is that basically, if you want to take the inverse, if you want gh times something to be the identity, if you take g inverse and then h inverse, then what do you do with this? That might or may not be true. But if you do it in the other order, then it's very nice. H inverse are right next to each other, so they cancel out. And then all you're left with is g and g, because the identity just goes away. And then all you're left with is g and g inverse. And they cancel out, and you're just left with the identity. So this will be relevant. And so let's think about this modular arithmetic. So there's a certain property of modular arithmetic And let's pretend for a moment that we don't know that, yes, as Brian says, nz is the set of all multiples of n for a positive integer n. And in particular, you can think of z itself as 1z. So now let's pretend for a moment that we don't know that addition is commutative, because like, oh yes, this is a good way of thinking about it. As Brian says, you know, if you put on your shoes, no, sorry, if you put on your socks and then you put on your shoes, the way to undo this is not to take off the socks and then take off the shoes. You have to undo first what you did last. So if you put on the socks and then put on the shoes, you take off the shoes and then you take off the socks. And so this is, you know, pretty much the same thing, but in math notation. So let's pretend for a moment that we don't know that addition is commutative, because like I want this to sort of give intuition for what's going on in a general group. So if I have this, I want this to be true. Whenever I add anything, well, I want on the left, I want it to still be true. So if this is true, I want this to be true. C plus A plus the inverse of C plus B should be in NZ. And now we know this is negative B plus negative C. But like, we don't know this would be true if we just took any old subgroup. So let's do this all again in a general group, but let's say we have a normal subgroup. And so I should define what that is. And consider this as sort of motivation in a way. So if I have a group G, so then, and I have a subgroup H. So then H is a normal subgroup if we have the following property. For any element G of the group and any element H of the subgroup, G times H times the inverse of G is in H. This looks weird, I know. But this is an important concept because this is basically motivation. Because let's pretend we're doing the same modular thing again, but in this group. So, because in modular arithmetic on the integers, if you know that two things are congruent mod n, and then you add c, you can conclude that you can conclude this from this. And so in line with our definition of modular congruence, let's define sort of congruence. Let's define congruence modulo this subgroup as this holds, and this is not standard notation, but it's for learning purposes for today's talk. If we have this is in H, and this is in line with what I said earlier about like A is congruent to B modulo n, which you can think of as sort of modulo the subgroup NZ, which I'll put in quotation marks, because this isn't standard notation. If A plus the inverse of B, which is A minus B, is in NZ, i.e. is a multiple of n. So this corresponds to what you know. But to have this, I want to have that this will imply this for any element G of the group. And I know it might be confusing that I'm sort of bouncing back between using sort of this juxtaposition that you would think of as multiplication and addition, but sort of just think of addition as a special case of think of this as just the operation in any group, and the addition on the integers as like a special case. So I want this to hold. And so what I need to be able to deduce that this implies this. No. But now look, this G2 inverse is G2 inverse G inverse. By what we said earlier about the shoes and the socks, you know. Or actually, let me not confuse you too much. So, okay, we have this. And so we can, the inverse of G2 is the inverse of G2 times the inverse of G. And we know it's associative, so we can just get rid of those parentheses. But now look, if we're assuming that H is a normal subgroup, then we have this. You can call this element G1, G2 inverse our lowercase h. And now this element, this is exactly H. And so we know that G inverse is in H. And so this modular congruence would have this nice property. And so it turns out that this works really very well. This sort of generalized modular congruence. And so what you can do now, is basically this sort of congruence modulo H, if you will. This will give us a relation on the elements of G. And it turns out that this is an equivalence relation, which basically, I won't get into the formal definition, but it basically means you can sort of divide up the elements of G into classes that are, and have it be like two elements are equivalent modulo G if and only if they're in the same class. So an example would be, if I have the integers and I have a subgroup 5z. One thing and now, is this a normal subgroup? Well, any subgroup of an abelian group is normal, because like you could just think, because if the group is abelian, then this GH inverse, if it's abelian, that's HG G inverse, because you can commute G and H. Then the GG inverse goes away, and you're just left with H, which is in H by our hypothesis. So any subgroup of any abelian group is normal. So in particular, the set of, multiples of 5 is a subgroup of Z, so it's a normal subgroup. And so we can consider congruence modulo 5Z, if you will. And it turns out you do get these equivalence classes, which you already knew. They're, equivalence classes modulo 5. You already knew this. This is just sort of a more general formulation of what you already knew. You have the set of all integers congruent to 0 mod 5 and congruent to 1 mod 5. Oh, oops. You didn't see that. Congruent to 1 mod 5. And the set of integers congruent to 2 mod 5 and 3 mod 5 and 4 mod 5. And so this breaks up Z into all these equivalence classes. And now here's the really, and so you could do this for a general group and a general normal subgroup. And now here's in fact, you could do these equivalence classes for a general group However, what comes next, you need a normal subgroup. You could do this for a general group and any subgroup, these equivalence classes, but for what comes next, you need a normal subgroup. Because what I want to do is I want to turn these equivalence classes, which are called cosets. I can take the set for a group G and a subgroup, I can take these equivalence classes, or I suppose technically these would be called right cosets based on how I defined it. But for a normal subgroup, the left and the right cosets are the same. But for assuming it's a normal subgroup, you can take the set of these equivalence classes, these cosets. For a normal subgroup, you can take the cosets, and you can make the set of cosets into a group. And this sounds really weird, I know. But this is sort of what you already knew. If you have, the integers modulo 5 are a group under addition. 3 plus 4, or I should say, you can sort of think of the whole set of integers congruent to 3 mod 5. Or how do I say it? Basically, you can look at the integers modulo 5 as just like the equivalence class of 0, which already is like brackets 0, and the equivalence class of 1, and the equivalence class of 2, 3, 4. And then you can make this a group, which is just the integers modulo 5, which you already know how to do. And the way you make it a group is just if you have, the coset of something A and the coset of something B, well, you do the most obvious thing, and you make it the coset of AB. And if H is a normal subgroup of G, this turns into a bona fide subgroup. Not a bona fide subgroup, but a bona fide group. And we call this G mod H. This is a quotient group, also known as a factor group. But the Wikipedia page is called quotient group, so, we'll say quotient group. And so, an example would be this same old thing, Z mod 5Z. The integers modulo 5, like Z modulo 5Z, which is the same thing as, just the integers modulo 5 under addition. And this is exactly the same thing as you already know. You would say 3 plus 4 is congruent to 2 mod 5. And to do this, you would just do the same thing. To take the class of 3 and the class of 4, you add 3 and 4, and you get the class of 3 plus 4, which is 7, which is the same thing which is in the same class as 2. And so you get this group G mod H. And, then you can really take off from there. But I don't want to go into that too much right now. So it's already 4 o'clock, so I'm definitely going to go over the expected time, but I understand if you have to go, because this is being recorded, so don't worry, you can expect a recording and eventually a handout. So, if you have to go, I understand, but, please stay. Thank you. Stay if you, reasonably can, but if you have to leave, I understand, because it is 4:01 now. So I understand if you have to leave, but, please stay if you reasonably can. And so, what was I saying? So we have these quotient groups, and so this is an example. So this Z mod 5Z is an example of a quotient group. Now, in a special case, if we assume that G is a finite group, if G is finite, then of course H will be finite. Because, a subset of a finite set isn't going to be infinite. And so it turns out that every coset, it turns out, in this case, will have the same number of elements. And actually, you could do this. You could make the cosets, I'll say in this case, you would make them like you could do, basically, when I told you about this modular congruence stuff, basically, when I told you about like A is congruent to B modulo n, I basically told you this was the same as writing like A plus negative B is in NZ. But the other way I could have written this is negative B plus A is in NZ. And of course, for addition, you get the same thing either way. But for a general group, if you have a subgroup, if you have a non-abelian group, a subgroup that isn't normal, you might not get the same thing. And the two ways you could get it, you would have them as like right cosets and left cosets. But this would work either way. So I'll just say, for example, every right coset will have the same number of elements. And it will be the same number of elements as H itself, because H will be one of the cosets. And so, but these cosets partition the whole group. And every coset has the same number of elements as the smaller group. And this tells you that, and you would, want to write out proofs, but I'm not going to bother to do that in today's talk. This tells you that the number of elements in the smaller group divides the number of elements in the number of elements of the subgroup divides the number of elements of the group. Because, imagine if you say, as an example, say the number of elements in H is 4, then I've divided the whole group up into these 4 element sets, with every element of the group in exactly one of the sets. And so I partitioned the group into 4 element subsets. So it's the number of elements, it would be divisible by 4. And this is the same reasoning as in general. So and we would say the number of elements in a group is its order. So what we're saying is the order of a subgroup of any finite group is a divisor of the order of the group as a whole. This is known as Lagrange's theorem. Okay, so now these factor groups are the subject of something that's, a really nice thing called the fundamental homomorphism theorem, which you should look up, but I'm not going to do that today. And when I say homomorphism, this is sort of a map between two groups that sort of preserves the operations in a way. It's sort of like linear transformations when we did last week, but sort of more general. And so these factor groups can tell you things about stuff related to homomorphisms, but I'm not going to get into this, but you can look up, I'm not going to get into this in today's lecture, but you can look up the fundamental homomorphism theorem. So yeah. One thing I do want to mention is that if a group, so obviously for any group, one example of a normal subgroup would be the entire group. Another example of a normal subgroup would be just the set containing just the identity element. If a group has no other subgroups, then we say it is simple. Oh, sorry. These are the set containing just the identity and the set containing the whole group. Those are examples of normal subgroups. So if a group has no other normal subgroups, then we say it is simple. So some examples of simple groups could be the integers modulo any prime under addition. Because this group has no subgroups other than the whole group or just the zero. So it doesn't have any other normal subgroups. So this is an example of a simple group. Another example of a simple group, it turns out that the alternating group, AN, is simple for n greater than or equal to 5. So, and now here's the big thing. With a very large amount of work, mathematicians have classified all finite simple groups. And so basically you get these groups, the integers modulo a prime, and the alternating groups, and then there's like another infinite, there's like another infinite family, or maybe multiple infinite families or something like that, but like there are more infinite families, or maybe just one more infinite family. But the point is there are some infinite families as a whole. Like, for example, this is an example of an infinite family of finite simple groups. And then there are some just exceptional cases that don't really fit into any of the infinite families. And the largest of those weird exceptional cases, of which there are only a few, there are like 26 or 27 of them, depending on who you ask, because there's sort of a degree that there's, you know, some people will, there's a certain group that some people say should be called one of, you know, maybe not everyone agrees on whether or not you should call it one of the exceptional cases, or whether it sort of more falls into one of the infinite families, but that's sort of just a disagreement over naming, I guess, or something like that. You can look it up. A lot of this stuff is on Wikipedia. But the largest of those sporadic groups is called the monster group. And it has the monster group. And it has a very large number of elements. This is how many elements the monster group has. Now you see why they call it the monster. So yes, this is a large number. And so when I say, you know, they've classified all finite simple groups, there is a concept of sort of isomorphism when two groups are essentially the same. You know, I could have a group of, oh, here's a group, triangle, circle, square. Oh no, triangle, square, circle. And maybe I want to say, you know, triangle plus triangle is triangle, etc. And maybe they just behave like exactly as if they were the integers modulo 3, and maybe triangle plays the role of 0 and square is 1 and circle is 2 or something. And so basically you would consider this to be, so maybe, you know, circle plus, I mean, why do I keep saying square when I write circle and circle when I write square? Maybe square plus square would be circle. And then, you know, maybe circle plus square would be triangle, etc. So the point is that this group is basically exactly the same thing as the integers modulo 3. I don't care whether I call it 0, whether you don't really, mathematicians, like, it's not that important. Whether you call the elements 0, 1, 2, or whether you call the elements triangle, square, circle, for the purposes of group theory, in the sense that it's exactly the same group, regardless of whether you call them this or that. And so you would consider it to be isomorphic. It's exactly the same thing. So isomorphic. And so basically they've classified all, basically they said any finite simple group must be isomorphic to one of these groups on this list, basically. And the thing about this is that basically you can think of the finite simple groups as sort of the building blocks of all finite groups. Because basically, if you have a group, and then you take a normal subgroup, if you have a group G, and then you take a normal subgroup H, well, take H and then take G mod H. And then just, you can keep, maybe then you could take a normal subgroup of G mod H, maybe it's called J, and then, you could take G mod J and then G mod H, mod J, or maybe there's K, and then you have K and H mod K or something. And the point is you would keep going until you got to some simple groups. And then basically there's a theorem that I think should tell you that the Jordan-Holder theorem, and there's probably 2 dots over one of these O's, and I think this theorem tells you that basically you could do this in multiple ways, but you always end up with the same simple groups at the bottom, the same building blocks. And so you can think of the finite simple groups as the building blocks of all finite groups. However, you should note, and so this is sort of like, this is sort of like how prime factorization of integers is unique. If I have 60 and I factor it, I think we should say bye-bye to the number of elements of the monster group now. Okay, bye-bye, monster group. But basically, you did this in grade school or whatever. If you add 60 and then you do this, and then you do this, you get 2, 2, 3, 5. Or if I wanted to start with 6 and 10, you get the same thing, 2, 3, 2, 5. Or maybe I wanted to start with 5 and 12, and then, split 12 into 4 and 3, etc. The point is you get the same prime numbers, but maybe in a different order. And similarly here, you get the same simple groups. And of course, they'll be finite, just maybe in a different order. And so you can think of the simple groups as sort of the building blocks of all finite groups. The finite simple groups as the building blocks of all finite groups. However, there is a weird phenomenon that having the same simple groups in the sort of the decomposition, I guess you could think of it, isn't necessarily the same group, which doesn't hold for the integers. If I have an integer and I tell you, oh, I factored it into prime numbers and I got 2, 3, 7, and 2 again, it has to be, 2 times 3 times 7 times 2, 84. With groups, you can't tell from just the simple groups, you can't necessarily tell what group you ended up with, what group the starting group was. And so that's sort of a weird thing. But yeah, and so that's about all I have to say about groups. And that alone took me like an hour. And as I said at the beginning, if you have any questions, please direct them to Brian. Justin and Naveen, I guess they left or something. But Brian is still here. Oh no, Naveen is still here, I guess. But yeah, if you have questions, you can direct them to Brian, not to me. Yeah, so please direct all questions to Brian, not to me. Thank you. And so, but there's a lot more to abstract algebra than just groups. I spent all that time talking to you about these structures called groups, and groups have only one operation. So what if I had 2 operations? So you can define a ring. A ring, basically, is a non-empty set R, complete with 2 operations, which we'll call addition and multiplication. And so there are several axioms, which are, first of all, just under addition, it is an abelian group. So you really want, well, in mathematics, mathematicians are willing to tolerate multiplication not being commutative. But really, almost all the time, if something is called addition, you really want that to be commutative. So that's sort of, a difference between addition and multiplication. And then you need multiplication to be associative. So A times B times C, And then you need the distributive property to hold. So A times B plus C is A times B plus A times C. And you know, A plus B times C is A times C plus B times C. And so an example of a ring would be the integers under normal addition and normal multiplication. Maybe some sources for the axioms for a ring will tell you it has to have multiplicative identity. Strictly speaking, I guess that's not necessary, but most rings do. So but yeah, this book I have here doesn't require rings to have identity, but you know, just don't worry about that. But you know, lots of rings do. And so an example of these a ring would be, you know, addition under multiplication and subtract under addition and multiplication. And I don't even have to explain this to you. You already knew that multiplication was associative. You already know that the distributive property holds, you know. And so, you know, but multiplication in a ring need not be commutative. But yeah, and you know, so yeah. One thing I will briefly mention about rings is that an example, factorization, is interesting in Z. You know, it's like you can uniquely factor an integer into prime numbers, basically. Modulo, you know, considering whether or not you have 1 or -1, or, you know, and then 0 is just annoying, but like basically you have sort of unique factorization, the fundamental theorem of arithmetic. And so you can consider sort of rings in which you have something like this, you know, unique factorization domains, and they have some properties, and you know, you can abstractify that too, but you know, no need to spend too much time on that right now. But you know, these things exist. And also with these rings, you can have a subring, a smaller ring that is itself a ring. And you can imagine, you know, that. Now imagine wanting to take factor rings, like or quotient rings, sort of like factor groups, but you want it to actually be a ring. And so you know, it would have to be a subgroup under addition, and then since we said it's an abelian group, it'll automatically be a normal subgroup, and so it'll be a group under addition. But if you want it to work under multiplication, it needs to not just be a subgroup under addition. It needs to be an ideal, which has some additional properties, which is like so an ideal of a ring is a subset, is an additive subgroup with the property that any element of the ring times any element of the ideal, or in the other order, are in the ideal for any element of the ring and any element of the ideal. Thank you. Okay. Yeah, thank you for saying bless you. So yeah. And so an example of an ideal would be our good old friend NZ of Z would be an ideal. Because like it's an additive subgroup, and then anything times a multiple of n is a multiple of n, you know. An even number times anything is even. And so it's an ideal, and so you can make Z mod NZ into a ring. And you already knew that too. You already knew that you can multiply and add. You already knew that you can add and multiply numbers modulo n, integers modulo n. Yeah. So yeah, these are examples of rings. More examples of rings, as my book says, I guess, yeah, would be the rational numbers under addition and multiplication, and the real numbers under that and the complex numbers under that. So it turns out these are all not just rings, they're actually fields. So what is a field? A field is a ring and it has some properties. It's commutative. So basically the multiplication is commutative. It has an identity element for the multiplication. And then to be a field, we're going to demand that 1 does not equal 0. We're going to demand that you know, the multiplicative identity is not the same as the additive. Because if they were the same, then it would just be, you know, just have one element and it would be boring. Okay, and then we also want, yeah, we want it to be commutative and we want there to be a multiplicative identity that's not the additive identity. And then we want any non-zero element to have a multiplicative inverse. And so basically this is saying you can't divide by 0, but you can divide by anything else. And so, yeah. And so this, and yeah, we said multiplication should be commutative, and I think this should be the definition of a field. Let me check. Yeah, okay. So that would be a field. And so, you know, these are all examples of fields. And sometimes if you have a ring that's pretty well behaved, if it has, you know, if it has an identity that isn't 0, if it is commutative, and if it has the property that there are no sort of 0 divisors, basically this means that if the product of two things are 0, then one or the other is 0, or maybe both, then basically you can sort of write down, you can sort of formally construct a field from this ring, and this would be called an integral domain in this case. So of course the integers are an example of an integral domain. No big surprise. You know, you would expect the integers to be an integral domain. And so and so for an integral domain, you know, assuming, you know, as long as it's not just a boring thing that's just 0, you know, assuming that's not the case, when you have an integral domain, you can turn it into you can make a field out of it in the same way that you can make Q out of Z, which is just take the fractions. You just sort of formally write down fractions, and then you sort of have to say that you can, like, when are two fractions equal? Well, you know, 4/6 equals 10/15. You want this to be equal so that you just say, well, they're equal if well, we know 4 times 15 is equal to 6 times 10. So let's make these fractions equal. And it turns out this will give you a field, the field of fractions or the field of quotients of the integral domain, as the book says, I guess, something like that. And so, yeah. So this is another thing. And so if you know, you can make the rational numbers out of the integers, basically. And one interesting thing about fields is that you can have finite fields. So an example of a finite field could be the integers modulo any prime. And so you might wonder, are there other, is this basically all there is? And the answer is no. And the answer is quite interesting. For any prime power, for any prime p and any integer k, at least 1, there is a field of that order, and it's unique up to isomorphism. And again, isomorphism is basically when two fields are sort of basically the same. And so this is quite interesting. And so you can look that up or whatever. But like as a weird example, imagine you have this. So the integers modulo 2 are a field, just 0, 1, basically. But now let's add a new element alpha and take this modulo 2, and alpha behaves modulo 2 as well. So alpha times alpha, alpha plus alpha is 0. But let's add an additional element alpha with the stipulation that alpha squared plus alpha plus 1 equals 0. And then like do algebra as normal. And it turns out this turns out to be a field. It's really, you might be kind of surprised. This is kind of a weird thing. And so you can have these finite fields that are kind of strange. And they have the nice properties. Basically, the field of order p to the k is like basically you can think of it as the roots of the equation x to the p to the k equals x, sort of. And then there's nice stuff or whatever. And you can have vector spaces over general fields, and you can sort of even generalize those to have something called modules over a ring. Something called a module over a ring. And those are studied, but I don't plan to get into those today, but you should look those up, I guess. And that motivates something called category theory, which is, very smart, which I don't plan to get into today. But yeah, and then there's more stuff, but I guess I'll just stop there. So thank you all for coming. And I guess that's all. So thank you all. Bye. Bye-bye. Okay. So, and yeah, if you have any questions about whatnot related to our, if you have questions about stuff, you can write to us at mathdivulged@gmail.com, and of course, you can look at our website, mathdivulged.com. So, bye-bye. And one other good thing I want to mention before ending the meeting, the book called, which I've mentioned before, if you look up An Infinitely Large Napkin by Evan Chen, which is, I believe, available for free online legally. And this has good stuff about lots of stuff. And probably some of the stuff I said today should be in there, I think. So this is a well-written book, I guess, so you can look up this. So yeah, and it's nice that you can find it freely online legally. So yeah, so thank you all for coming, and I guess I'll just end the meeting for today. Thank you, bye-bye, goodbye. So, oh yeah, Brian sent the link, so I guess I'll end the meeting for today. Thank you, bye-bye.